In this lesson, we're looking at inverse functions. And so we start just by reminding ourselves what a function is. A function was a relationship between an input and an output, where we assign each input exactly one output. So if I put in a -3 into this first function, 2x plus 1, I will always get out a -5. Every input has exactly one output. That happens in each of these functions. These are all different representations of various functions. The inverse of a function would be going the opposite way. So we would want to ask ourselves, if we were told what the output was, could we figure out what number was the input? Let's look at that first function mapping. So this first function, if I was told that the output was y equals 5, we could figure out and infer automatically that the input had to be 2. So we would say then x has to be 2. We can look at the last graph, this last function, and think about, well, what if we were told that, in this case, y equals positive 2? If y was equal to 2, we can see that the function is equal to 2 twice, once at 0 and once at positive 4. So here we would say then x would equal 0 or x equals 4. But because there are two options, I can't figure out exactly what number had to have been the input. And that is what makes that trickier. So a function that is 1-to-1 will have an inverse. A 1-to-1 function is a function defined on a specific domain that is 1-to-1 if each value of f of x corresponds to exactly one value of x. Now that's just another way of saying each value of y came from exactly one value of x. These are easier to determine graphically, but a one-to-one function passes the horizontal line test. And we write that function out using the unique inverse function notation. So if f is a 1-to-1 function, then it has a unique inverse, and we write it with f to a little -1 superscript. Now that's not an exponent, so it's not a power, but it is a superscript, similarly typed how exponents are typed. We often write it with the of x part for function notation, so it's the inverse function f of x. In this first example, we're going to let f of x be this mapping diagram, and we want to look at how does the inverse function look if the inverse takes this backwards. So if the -4 is mapping to 0, the inverse should say that 0 came from -4. So we could redo this mapping diagram and make that 0 go back to the -4. -2 maps to -3, so the inverse would take that -3 back to the -2. 1 mapped to 9, the inverse maps 9 back to 1. 7 mapped to 6, so the inverse takes 6 back to 7. And lastly, the 8 mapped to 2, so 2 maps back to 8. Our inverse mapping diagram would look something like this, and we can see that all of these outputs are mapping back to their original input. A 1-to-1 function f usually takes this domain to some specific range f. The inverse takes that range back to the domain. That range of f becomes the domain of the inverse, and the range of f inverse was the domain of f. In example 2, we have a collection of points. Those coordinates can be represented as a mapping diagram like we saw, or like a set. We describe that similarly, saying if -6 mapped to 2, the inverse would be 2 mapping back to -6. So the inverse set would say 2, -6 is one of the coordinates, and then 5, -3 is another coordinate, 8, 0, and 11, 3. There's our inverse for that set. If we look at a graphical representation, I've got 4 different graphs here, and we just want to explore for a moment and see which one of these graphs, or maybe multiple, which graphs do you believe have an inverse and why? So if you want to pause the video real quick and just make a guess, an educated guess of which ones you think will have an inverse, and then resume when you're ready to discuss it. Okay, so if I look at this first graph, graph 1 does have an inverse. In that graph, each output, which is y, comes from only one input. So every value of y comes from exactly one value of x. We can look at that as a horizontal line test and think about, if I drew a line at y equals 8, that is going to intersect the function one time, meaning there's only one x value that produces an output of 8. In graph 2, we could draw a line at +1 here and see that this intersects the function twice. So there are 2 x values that give you an output of 1. This would fail the horizontal line test. So this would not be a function. In fact, graph 1 is the only one that does represent a function, because the other 3 graphs would fail that horizontal line test. So we can say that graph 1, it passes the horizontal line test. So take a moment to draw some graphs of your own. See if you can create a graph of a function that would have an inverse, and then another graph of a function that would not have an inverse. Try not to use the same ones that we just saw. For these, your graphs that would have an inverse have to be 1-to-1, so they have to pass the horizontal line test. That could be a square root function. That passes the horizontal line test. It could be a variety of things. So see if yours that you drew does pass that horizontal line test. For something that would not have an inverse, it just needs to fail the horizontal line test. I'm going to abbreviate that HLT. An absolute value function fails the horizontal line test, but there are a lot of graphs that we've seen that would fail the horizontal line test. Down at the bottom, we have another set of coordinates. So we have some other sets for a function, f, and for g. We want to write out the inverse of that function as long as the function is 1-to-1. Remember, if something is not 1-to-1, then it does not have an inverse. So I'm going to look at f first. We have 4, -5, 6, +1, 2, 4, and 0, -3. For it to be 1-to-1, each value in y has to come from only one value of x. So if I look across the coordinates, -5 is a value of y, and it only comes from +4. +1 is a value of y, and it only comes from +6. So if I do that for each coordinate, f is 1 to 1, so it would have an inverse, and we would write f inverse as the collection of points that are the inverse points. So -5, 4, 1, 6, 4, 2, and -3, 0. Then if I look at b, we have the function g. -5 is coming from only +4. We have a point 6, 0, so the output 0 is coming from 6, but I see in another point the output of 0 is coming from 1. So this would not be a one-to-one function. G is not one-to-one. So G does not have an inverse function. So in the next couple of videos, we're going to explore inverse functions more. We're going to look at how do I describe them graphically, and then we're going to find the inverses algebraically. So go ahead and start up the next video on graphing inverse functions.